The log flume originated from the need for cheap, fast transportation for lumber from where it was felled to where it could be used. The first V-shaped log flume was created by James W. Haynes in 1868. The longest log flume was the Kings River log flume, created in 1890 in Sanger, California. It was over 100 miles long. The log flume helped open up mountainous areas for lumber production. Where teams of oxen and horses could not go, water could. It could carry wood over steep hills, gorges, and other obstacles. The first riders were, of course, those who worked with the lumber and the flumes. It was extremely dangerous, though. The modern ride we know and love is infinitely safer than those original spur-of-the-moment rides down cliffs on freshly felled trees.
Sawmill Plunge opened at Lake Compounce in 1986. Built as a classic log flume ride, riders begin the ride going up a huge incline to get to the necessary height for the drop. Next, the riders traverse through the trees just as the logs did in the original log flume system. Finally, the riders are dropped down a slope to mimic the logs being dropped into a sawmill. Now for some givens that we were able to find. The length of the log flume was measured to be 2.75 meters. The vertical height for the final drop is 14.9 meters. The time it took for the log flume to travel the length of itself, 2.75 meters, is 1.93 seconds. The mass of the boat is 158.76 kilograms and the angle of the drop is 40 degrees. Using conservation of energy, we can calculate the maximum velocity the riders will experience. This occurs at the bottom of the drop. Conservation of energy states that the initial mechanical energy equals the final mechanical energy. Thus, the initial kinetic energy plus the initial potential energy equals the final kinetic energy and the final potential energy. The final potential energy equals 0 because at the bottom of the drop, we assume height is 0. Now we can write out the equations for the energies and solve for symbols to find V2, which is the final or the maximum velocity. Now we must find the initial velocity before the drop. So we know that the log length is 2.75 meters long and the time it takes for one log length distance is 1.93 seconds. Velocity is distance traveled over time. We can plug in our numbers and find that the initial velocity is 1.42 meters per second. After finding the initial velocity, we can find the final velocity. From before, we measure the vertical height of the drop to be 14.9 meters. Now, we plug in the numbers into the equation where we solve for V2 and we get a maximum velocity of 17.2 meters per second. To put that in perspective, you can travel this speed down Route 10 and keep up with traffic. Of course, this maximum velocity is an ideal estimate. In reality, friction and drag will slow the speed of the log down. In this calculation, friction is ignored, so the maximum possible velocity is calculated. There are also multiple forces acting on the log as it goes down the drop. Here we have a force-free body diagram. The first force is weight due to gravity. This force is always straight down, no matter at which angle the object is at. It is also denoted as mg, which is the equation to solve for it. Next, the angle of the drop is added. We can then split weight into its component pieces, mg cosine theta and mg sine theta. The normal force is perpendicular to the tilted x-axis. The drag force is behind the object in the direction opposite it is traveling.
A drag force is a resistance force caused by the motion of a body through a fluid, such as water or air. A drag force acts opposite to the direction of the oncoming flow velocity. This is the relative velocity between the body and the fluid. The drag force is modeled after the equation D equals 1/2 c rho a v squared, where c is the drag coefficient of the object, rho is the density of the fluid, a is the cross-sectional area, and v is the velocity of the object. As this relates to log flume rides, the drag force slows down because it is a resistive force acting directly opposite of the object's motion. Buoyancy is the upward force needed to stay afloat, and it's measured by weight. Buoyant forces are why we feel so much lighter when we're in a swimming pool or bathtub. Our bodies are mostly water, so a person's density is fairly close to that of water. It was Archimedes that figured out what causes buoyancy. Archimedes figured out that if the weight of the object being placed in the water is less than that of the weight of the water being displaced, the object will float. This is known as buoyancy or the Archimedes principle. As this relates to the log flume rides, the buoyancy force is directed upwards against gravity when the log flume is in deep water, which allows the raft to travel above water.
Water rides like Sawmill Plunge involve the concept of relative velocity. The velocity of the log flume relative to an observer standing on unmoving ground will be equal to the sum of the velocity of the log flume relative to the water and the velocity of the water relative to the ground. So the log flume will appear to be moving faster to the observer on the ground than to the person on the log ride, because the velocity of the water relative to the ground will not be considered for the person on the ride.
Of course, doing stupid and dangerous things with water never gets old. People used to go over Niagara Falls in wooden barrels, but the second person to survive going over Niagara Falls, Bobby Leach, did it in a steel barrel in 1911. And 15 years later, he died from a gangrene infection in his leg, which he broke from slipping on an orange peel. The newspaper remarked that he might have been safer in the barrel. Water parks like lake compounds let us fulfill our inner desires to go over steep slopes at great speeds, both with or without water, relatively safely. Just think, if we didn't have water rides, how many more people would die from doing reckless things?